Good morning, everybody, and welcome back to AB Calculus BC Live, the only place on the internet where a genius problem writer who gives bad haircuts and a washed-up 80s cover band guitarist who does terrible Grover impressions will work out BC Calculus questions for you for the next 50 or so minutes. I'm joined today by my great friend, Brian Passwater, as usual, and today we're going to talk about graphical stems connecting AB with BC. And as always, we want to make sure that you know that you can download all of the files associated with today's activity. Follow along with us by going to the Dropbox, printing that out, and working those along with us. As I said before, Brian Passwater, Speedway High School's finest, is with us as always. And Brian, how are we doing today?
Tony, I'm doing great. How are you?
I'm doing fantastic.
Can we practice our high five real quick? Because we weren't doing a great job of it yesterday. I want to practice it, see if we can get this thing figured out here real quick. So
that was pretty bad. Let's go.
All right, 1, 2, 3, high five. All right, that was worse. We're gonna practice. I can't tell who needs more practice, us on this. It's probably me, yeah. But I realize now why you were doing the intro today. I've been doing the intros the last couple of days, and each time I do an intro, I put you on the spot. I think I just realized you were thinking if you intro it, maybe you can gloss over the fact that yesterday, if students weren't watching, I promised that if we can get 50,000 students watching this week's videos, because that's how important they are, that I'm going to literally find a way to pie you in the face virtually. But it's going to happen. It's going to happen. I'm going to get you pied in the face. So students, get your other BC friends joining and getting on there so we can get Tony a pie in the face. But I am ready for today, Tony. I even got my shirt on. This is my wife got me this shirt for Father's Day that says "A day without math is like just kidding. I have no idea," because literally every day of my life is pretty much doing mathematics stuff. So I know I'm ready for today's lesson on graphical STEM. Tony, every time I'm talking, I always feel like you're not listening to me. What do you got? What are you messing around with?
Oh, I'm sorry. Well, today's lesson is about graphical stems. So I went out to my garden and I plucked this. It's a graphical stem, and I thought we could use this today. I thought this could be pretty helpful to, invoke in our lesson a little bit. Graphical stem. I've got a tabular stem row. They weren't quite ripe yet.
No. Not literally a stem. When we're talking about graphical stems, every AP problem has some introductory information, like a table or a graph or something we give students up front. We call that a stem in the calc world, right? That's the stem of the problem, not a literal stem.
Oh, so we don't need the algebraic stem tomorrow then? They're ripe. They're ready to pick.
No, I think you can save those for whatever you're using those. I don't even know what seeds you would buy to get those to work out, but no, we're talking about just different types of problems the students might see on the exam. So I'm a little bit worried now. Like, are you ready for today?
I'll tell you what, I'll give it a shot. I'll give it a shot.
Okay, because you're leading us off today.
I'm leading us off. Oh, goodness.
Problems, so.
All right. Well, let's give this a shot nonetheless. So as we said, our topic today, graphical stems. So within the stem of the problem, within the preliminary information, you're certain to see some type of a graphical representation from which we would extract data and move about through the problem. So our BC1 today starts with a graph of f prime of x. And the graph of f prime, the derivative of the continuous function f, is given above. And for -5 less than or equal to x less than 4, the graph of f prime consists of 4 linear pieces and a quarter circle centered at 2, 2. For x greater than or equal to 4, f prime of x is -2 e to the 4 minus x power. And it is known that f of 0 is 6. Our job is to find f of 4. And we've talked about problems like this here before. We really have focused quite a lot on the fundamental theorem of calculus lately, but there's so many different ways that you can sort of perform these integration techniques, these integration ideas, and this is going to illustrate one of those forms just yet again. And the idea is, if you want to find information about f, and you're provided with information about f prime, it seems very logical that we would want to perform an antiderivative, that we would want to perform some kind of integration process. And that will be the same in this particular problem that if we do integrate f prime, we will get f. However, we have to do that with a little bit of help. And that help comes in the form of some boundaries. And given the fact that f of 4 is something that we want to find, it seems very logical that 4 should be one of those boundaries. Where will 4 get some other help? Read through the stem of the problem, and we see that we also know that f of 0 is 6. So 0 and 4 will really work well together to serve as our boundaries, and you would most likely want to put them in the logical order, 0 below, 4 up above. And we know that the result of this from the fundamental theorem will be f evaluated at 4 minus f evaluated at 0. And there's that f of 4 that you're going to need. And if you would like, you could go ahead and isolate him. And that's just a matter of adding the f of 0 over, which kind of brings up another interesting idea, especially when you talk about accumulation or sometimes with particle motion. You have this notion of trying to find a certain ending position, but you have to find that by starting with this beginning position and then adding some accumulation, right? Some accumulated change. And that's really what we've developed here when we've reworked this particular formula. Now, this problem's not talking about motion. It's not talking about necessarily accumulating something in context, but the calculus idea is still there. So to find this f of 4, we would go ahead and figure out, first of all, well, what is this f of 0? Well, we were given that, 6. And then for the evaluation of this definite integral, we can move to the graph, knowing the graph is very well behaved. And by that, I mean consisting largely of segments and quarter circles, especially on the interval which we're analyzing, we can use a little geometry. So if we integrate from 0 to 4, what we've got on our hands, first of all, is this very unusual shape right here. If I sort of color this in this light blue, we have a very unusual shape that we're going to have to use a little bit of deductive reasoning here with and figure that we first of all have this 2 by 2 square that we can start with. And you've seen these before, I'm sure. And from that 2 by 2 square, we can subtract this area in white that I'm motioning towards, which is just a quarter circle that has a radius of 2. So that would be a 1/4 times that pi times that radius squared. And now we're off to find the area from 2 to 4, which looks like we've got this orangish shaded region here, which is nothing more than a triangle. However, that triangle located below the x-axis means that we're going to have to give it this negative signed area. And so we want to make sure that we employ that. And then we have the 1/2 base times height formula, 2 times 2 in this case. And then if we want to simplify this all up, we would get 6 plus 4 minus 1/4 pi times 4 is just pi. And then 1/2 times 2 is just minus 2. And then when all is said and done, we have 8 minus pi. And this 8 minus pi is actually going to play a role in some future problems, maybe not the ones that we do necessarily with you, but when you take a look at maybe BC3, BC4 later on, we're going to reuse these stems and ask some different questions. So you want to kind of hold on to that particular response as it'll come back. All right, so let's take a look at part B. Part B is going to bring to the front a BC topic here. Write but do not evaluate an integral expression that gives the arc length of the graph of f from x = 4 to x = 10. Now, if you recall, our arc length discussion really wasn't all that long ago when we talked about how it would be asked on the AP exam this year, only in the environment of sort of the rectangular coordinate plane. And that would just simply be a matter of integrating the square root of 1 plus the derivative of whatever your function's name is squared with respect to x along a couple of given boundaries. Well, it's uncanny how in this particular problem, we are not going to really deviate from that formula. So this problem here would just test one's ability to really remember what is this formula of the arc length. So we would just simply set this up. You can call the arc length L, S, anything that you'd like. We're given the boundaries over which we're integrating, 4 to 10 in this case. We have our square root, 1 plus, And then we have to think about, okay, what is our f prime? Well, I got an f prime graph up here, sure, certainly, but if you recall, in this particular problem, we're given a little bit more information about that f prime graph, especially on the interval that begins at 4. And so we have a much more specific way to represent that, and that is with this -2e to the 4 minus x. Now you want to be very vigilant about this and not try to take the derivative of this expression because it's already expressed as f prime. Now you will have to square it though. And honestly, by the time you get to that point, there's really nothing more that you need to do. Of course, you could simplify by performing that square to get a +4 and distribute the 2 in the exponent and get 8 minus 2x, but it's really not necessary. You've answered the question that's been asked. There's your arc length. And you're probably looking at this thinking, okay, well, why can't we evaluate that? Well, I have a feeling that that's going to be a pretty tricky integral to take by hand, so we're just going to leave it like that. And then for part C is one of my favorite parts of this problem. It's a little tricky here, and it can really get some kids into some trouble. So I'm gonna have to get ready for this, take a sip of water. Okay, that walk in the garden today really wore me out, picking up all those stems. So we have the summation of a sub n from 2 to infinity, and we're defining a sub n as f prime of n. Okay, so it sounds like we can just write out this series or think about this series, and the fact that we're asked to find it means that this series better be, let's say, findable, right? It better be the type of series that we can add all the terms up, and there aren't very many that are like that. So let's kind of get a feel for what this series might look like. So the summation as n goes from 2 to infinity, just who are you? Well, what he is just simply a series that allows you to plug 2 in for n in this f prime function. Start with 2. Okay, well, that would mean that our first term here is just really f prime of 2. Okay, well, I think I'm getting this. Then our next term would just be f prime of, you guessed it, 3. And then our next term would be f prime of 4 and f prime of 5. But as I start to think about that, by the time we get to 4, don't we have a little bit more information about just who f prime is, right? He's just this expression, -2e to the 4 minus, I suppose, n power now. So what I would suggest is that we write this as another summation, and we start him at 4, take him up to infinity, and just call him what he is, -2e to the 4 minus n power. Now you can see how one could really get into trouble with this, and not that this ever happened to me when I was rehearsing this problem last night, but you could very easily confuse the fact that this particular series or this particular expression right here could be your go-to expression even at the beginning of the series when n is 2 and n is 3. So we have to resist the temptation to do that. Now, as we start to answer this question, what do we notice? Well, f prime of 2, well, that's a pretty easy value to find just from the graph, that's 0. And f prime of 3 from the graph would be -1. So I'll say -1 there instead of plus -1. And then we see this guy. And we have to have some faith in this guy because there really aren't very many series, like as I said before, that we can add together. And on this particular AP exam that you're going to take this year, the geometric series is about the only one. So we have to look at this and think, well, is that a geometric series? Well, sure, you could continue to list the terms out. And it's not a difficult thing to do. And I think that if you do list the terms out, it would be very easy to find the first term and find the R value. And you could use that manipulation of the first term divided by 1 minus R. Another kind of clever, maybe more analytic way to do this particular problem is you could think about rewriting this just a little bit. Now, what do I mean by that? Well, just using a power rule in reverse. Your -2 just kind of stays where he is, but can't we say e to the 4 minus n is the same as e to the 4 divided by e to the n, right? Just working that power rule in reverse, right? When you divide like bases, you subtract their exponents. And then we could rewrite this expression, use good linkage here, and we could sort of extract the -2 e to the 4th out as sort of, I don't know, maybe an a value. And then what's left is 1 over e to the n, which I believe we could just write as 1 over e all raised to the n, sort of like that. And now we have that more typical form of our geometric series. Now you want to be careful, n doesn't start at 0, so it might be a little bit tricky to see exactly who is that first term. So we might be better off plugging 4 in to determine that. So we're just about there. We still have our +1. And now, if you recall, the solution to that type of convergent geometric series, and by the way, we do know that this series converges because the 1 over e is our r, and 1 over e, 1 over 2.7-ish, his absolute value is less than 1. That's important. But basically, you're just looking at taking the first term and dividing it by 1 minus your ratio, right? That's sort of the verbal depiction of how to figure out the sum. And so the first term would be, well, if I let n be 4, I have 1 over e to the 4, which, I think that that's going to cancel with that e to the 4. So I end up with -2 on top. And then 1 minus the ratio would be 1 over e. And of course, you could leave the answer like this. There's a variety of things that you could do to this. If you wanted to get a common denominator with that first or second fraction here, you could multiply through by an e, I suppose. Then you could get a common denominator among both of those. There's a variety of ways to do that. And maybe this could be your best looking answer if you wanted to go that far, but you want to be careful. There's really no reason to simplify, especially if it's going to put you in a situation where you could make an error. But you can practice that later on to kind of see how you can bridge the gap between my answer here and the simplified answer if you're curious how to make it look a little bit pretty. I think Brian is now going to lead you into parts D and E of this problem.
Perfect. So we're going to take a look at two more parts here at the end of this problem. And like we have in all of our materials, there's a whole bunch of extra problems. So I wrote a whole bunch of problems, and then we picked 5 to do on BC1 and then 5 for BC2. And then if you look in the files, you'll see 2 additional FRQs with the same stems, 1 for each, that you can see more problems that might appear. So what we try to do is create sort of a FRQ experience for you of what might appear on this year's exam. So we might see 5 parts or 6 parts on that first longer question, right? The first 25-minute question might be more parts that kind of span the whole course between A, B, and B, C. So we're trying to give you some of that experiences. And so we're going to look at just 2 more parts here. But if you look at the other problems that we're not going to do today that are at the end of this handout, you'll see more FRQs with similar questions, but it'll be different topics covered in the course if you want to practice those as well. So looking at part D, same graph of F prime, but notice for part D, we introduce a new function. Right, so for parts D and E, let's introduce a function g, where g is defined as 3 minus the integral from -1 to x of 2 times f prime of 2t plus 1. So it's kind of a lot going on there with g, but with only 2 FRQs to work with, I would anticipate on this year's test, we might see something like this, where they start you off somewhere in the problem, they give you some information about f or f prime, and then later on in the problem, they might introduce a new function that's related to that original function in some way in order to get all of these big important ideas covered on the exam. And so when that happens, just go with it and just say, okay, I've got g. Now, what do they want me to find? Well, they want me to find first, write an expression for g prime of x and g double prime of x. And so to find g prime of x, we have an equation for g. So all we need to do here is differentiate this, right? We have an equation, we can differentiate both sides of the equation. So on the left-hand side, g becomes g prime. And then on the right-hand side, if we differentiate, that 3 is going to go away and become a 0. And I'm going to go ahead and put a 0 there just because I don't forget to put the minus sign afterwards. And then we get to this part here. And you might have noticed every lesson we do, we've pretty much involved the fundamental theorem of calculus. Part A today that Tony was doing was the fundamental theorem of calculus. And then this derivative of an integral is also the fundamental theorem of calculus. There's two parts, but it's really the same thing. It's one big fundamental idea. And so we keep doing it every lesson because, as you can imagine, if we call it the fundamental theorem, it's probably going to be tested on the exam, right? This is the big theorem in all of calculus. And so we want to do this every day until it almost becomes so natural that no matter what twists and turns and little kind of interesting takes the College Board puts on it, you're ready for it. So each day we're doing a little bit different of a variety of one, but we're going to keep doing them because it's certainly going to be tested on the exam because of how important it is. So we're taking the derivative of this definite integral with x in the limit. So to do that, we talked about how we have the second fundamental theorem. It says we just plug that x right into our expression. So it's going to be 0 minus the quantity 2f prime of 2x and then plus 1. And you'll notice in this case, because we're plugging it in, we have to keep the entire expression the same. And I put it in brackets because this minus sign in the front is being, distributed to the entire expression. So be careful with your parentheses and your grouping symbols. Otherwise, you're going to forget that it's being applied to everything inside of there. So we could leave our answer like that. There's no need to simplify it. But if you did simplify it, if you didn't want to use the brackets and the 0, as long as your answer was equivalent, meaning it should have been -2 f prime of 2x minus 1, you're going to be okay. And then I want to make one more comment because we've been doing chain rule a lot with this second fundamental theorem. We're plugging in the value and then we're doing chain rule. I've made a couple comments in previous days about how when you're doing the second fundamental theorem, you don't want to look in the parentheses of what you plugged in. What happens is sometimes students will see that 2x and think, oh, I have to multiply my answer by 2 because of chain rule, right? Well, we are doing chain rule on this problem, but the chain rule is not what's in parentheses. The chain rule is based off of what expression you plugged into the parentheses. So we plugged x in, right, for t, which is where the 2x came from. The chain rule is multiplying by x's derivative, which would be 1 in this case. So be careful you don't multiply by an extra 2 just because you happen to notice that 2x in parentheses. So that'll take care of g prime of x, and then g double prime of x. Well, once we have our g prime, now we're just differentiating again, right? So we're looking at this expression and we're going to differentiate that. Well, we have an f prime, and we know that f prime of 2x, right? Kind of outside function, inside function, which is going to be a good example of chain rule. Wherever we're doing the chain rule, we take the derivative of the outside function. So f prime becomes f double prime. That's f prime's derivative. And then we always leave the inside piece the same. And then by chain rule now we are going to multiply by the derivative of the inside piece. So 2x's derivative becomes 2. Now the minus 1 is going to go away because 1's derivative is just going to be 0. And this is going to be our second derivative. And we could clean this up again if you wanted to and become -4 f double prime of 2x. And so that's kind of a straightforward conceptual idea of the second fundamental theorem, as well as a nice little simple chain rule idea. But these are the kind of problems that can be tested really well on an exam like this year because they're not just something you could type into a calculator. You're still using chain rule, you're still using the second fundamental theorem of calculus and all that good stuff, but it's not going to be so much with an equation that you're used to, like e to the 3x or 2x plus 1 quantity squared. It's going to be more in lines of a conceptual function defined by another function type problem. So let's jump ahead to part E, which is going to reuse some of that information that we just did. So I kind of wrote down some things here that we might need. But part E continues. So the same stem, the same G function, but we want to know if G has a point of inflection at x equals 2. And I've trained my students, whenever you're given some front-loaded information, like G has a point of inflection, I tell them before you start looking at the graph or the equations, or before you start even trying to involve all of the information that was given in the problem, look at just the question. We call it isolating and translating the question. So the question says, it's talking about G having a point of inflection. And so I tell my students, don't worry about the equation. Don't worry about the graph right now. Just think about if you only had this given to you, right? And you didn't have any other information. how would you tell if any function had a point of inflection? What would the process be? And so we call that building our roadmap to say, okay, how would I do this, right? What's my roadmap? And then we can go back to the information given to see how that information might apply. And that helps alleviate a lot of the confusion and students getting lost in the problem sometimes. So for a function, any function to have a point of inflection, really we're looking for two things to happen. Number one, the second derivative of that function needs to be either 0 or undefined. Those would be our possible points of inflection. But then more importantly, once we know that happens, the second derivative needs to change signs, right? It has to have a sign change in order to create that point of inflection. So this is sort of my roadmap, which means I'm going to first try to figure out when G double prime is 0 or undefined. And then once I do that, I can check to see if at any of those locations, we see a sign change in G double prime. So this tells me I need to be looking at G double prime. Well, fortunately for us, we have a function. And even more fortunately, we just told you where to look, right? We said check at 2. So I can just plug 2 into my expression or my equation for G double prime. So G double prime of 2, if I plug it in, it's going to be -4 times F double prime of 4. And I want to find out if this right expression is equal to 0 or undefined. Well, what do I have given to me? We're given a graph of f prime, and I'm needing to find f double prime of 4. So now we're having to make a few more connections, right? Where you're given a graph of f prime, we need to answer a question about f double prime, which is the derivative of a function. Well, graphically speaking, if we're trying to figure out the derivative of a graph, we should be thinking about the slope of that graph, right? The slope of a graph is going to be kind of equivalent to the derivative of the graph. And so f double prime, which is the derivative of f prime, is the slope at where? When x is 4. So if we go to the graph of 4 right here, we see this kind of a corner there, right? A sharp turn. It's kind of a cusp, but not quite. It's like a straight line and then a curve there. But it's a sharp turn. And so the derivative of f prime right there doesn't exist, right? Because there's a corner. And so we know that this is undefined or does not exist. It's an undefined value because of the corner. So that means it's possibly a point of inflection, right? But not guaranteed. Two things have to happen. I'll do the first one now, and then I'll make one kind of comment here at the end to be safe. And then with my students, we like to do a sign chart. And you might be able to look at the graph and skip the sign chart when you have a graphical example, but it's always helpful to go back to a sign chart. And so we have G double prime, and I know that 2, not 4, right, of 2 is my critical value that I'm checking on G double prime. And we know that's happening right here, right? It's when f double prime of 4. Well, if we look a little bit after that point, right, a little bit past when x is 2, we're going to be looking essentially right over here on the graph, right? And so the graph of f prime after that moment is increasing, right? The f prime graph is starting to increase right there, which means it has a positive slope or a positive derivative. And so a -4 times a positive derivative, right? Once we get past 4, we have a -4 times a positive value is going to give me a negative second derivative. And then looking a little bit before that value, we're looking on this side of the graph. Well, now we see this linear segment which has a negative slope. And so we have -4 still, but now the slope just before that value is going to be negative as well, which gives me a positive value, which does tell me we do see a sign change in G double prime. And so because there is a sign change, we want to assume that there is a point of inflection, right? But I want to point out one more thing. We have to be careful when you're finding relative minimums, maximums, or points of inflection, because all of those things, first and foremost, require there to be an actual point on the graph, right? You can't have a point of inflection if the graph doesn't have a point. And sometimes when you're doing analysis, we start looking at values that are undefined, which means in some cases, not only is the second derivative undefined, but sometimes even the original graph, right, is undefined, meaning there's a hole or an asymptote or something on the graph where it doesn't exist. And in those cases, if their original graph of G doesn't exist, there can't be a point of inflection or anything. So we want to be careful that there is an actual point on this graph. And here's how we know. The stem told us that F was continuous, right? So if f is continuous, then if g is the integral of f prime in this case, we're going to be defining g as some kind of function of f. So we know that g also is going to end up being continuous. So we just want to kind of double check there actually is a point, even though you see a sign change. And so here we can say, yes, there is a point of inflection at x equals 2. And the reasoning is going to be critical, and we're going to hit reasoning really hard on Thursday this week. But our explanation is going to be because G double prime changes sign. So there's a point of inflection on the graph of G because G double prime changes signs. And I can make that connection, even though I was using a graph of F prime to answer the question, I can still talk about G because we made that connection. Because I connected G double prime to F double prime and G prime to F prime, if you make those connections in the problem, then you're able to still talk about G in your reasoning. You could have also said because -4 F double prime of 2x changes sign, but that seems a little bit more complicated than just saying G double prime changes signs there. So that's going to be our answer to part E. And then Tony's going to get us started on a really cool FRQ. And we're going to try to squeeze in 6 parts. We'll see how well we do. We might have to cut one of these out, but I love all 6 of these parts. So I really hope we can get through all 6 of these today, because they really are great questions that will prepare you for the exam. So Tony, do you want to take us away on BC number 2?
I certainly will, and let's read this one together. We have a portion of the graph of the twice differentiable function f that's shown in the figure above. Something to note, now in this problem you have a graph of f, whereas in the previous problem you had a graph of f prime. The areas of the regions bounded by the graph of f in the x-axis for the closed interval -2 to 6 are shown above. At x equal -2, the line tangent to the graph of f is shown along with its equation. The function h is defined by h of x equal the definite integral from 0 up to x of f of t with respect to t. So our opening question is to evaluate this definite integral, f of 4 minus 2x from -1 to 2. And what we hope that you recognize is that this is a U-substitution problem, right? We have this sort of complicated piece within that function f, 4 minus 2x, that could certainly serve as our U value. And upon taking his derivative with respect to x, we end up with -2. And I could swing that dx over if I'd like. And what we notice here is this dx value here. If we wanted to do this, we could at least think it. We don't have to write it. But that dx value is just really du divided by -2. So if this guy was to get replaced, he would become du over -2. Now, what does that mean? Well, that means that we would have this -1/2 floating out in front of our integral. Now the function is f in terms of u with respect to that u, and we have to consider what we want to do about the boundaries. Well, I'm going to go ahead and suggest that let's change those boundaries in this problem, because you never know, we might need them to change in order to extract the information from the graph that's been provided. And changing the boundaries is a very easy task, because all we need to do is take this 2 and take this -1 and replace x with them and figure out what their new u values are. So let's see if I can find some room maybe over here to do that. U of 2 would just be 4 minus 2 times 2, which of course is 0. And u of -1 would be 4 minus 2 times -1, which would turn out to be a 6. Now, when you place those boundaries back in, make sure that they go into the correct spots. So if 2 has turned into a 0, then I'm going to still put that 0 up as the upper boundary, leaving the 6 as the lower boundary. I know that that kind of gives us a little bit of a backwards appearance for this integral, but it is the correct setup, and we can deal with that. And the way that we can deal with that, if you want to take care of that right off the bat, is we could extract the negative value out in front that then says that our boundaries can switch. If that makes things just a little bit easier for you, by all means, go ahead and do that. And now we can actually find the area under the graph f above the x-axis, or between the x-axis and the graph, between 0 and 6. And luckily, we have the information that's going to allow that to happen. Between 0 and 6, As you can see, we have a positive area of 3. This area below the x-axis as signed area would be -5, and this another area above the x-axis as 9. So we would end up with 1/2 quantity, and then we take 3 minus 5 plus 9. And once all the dust settles, if we choose to do some simplifying, I believe this turns out to be 7/2. And there's our evaluation of that definite integral. Moving on to part B. Part B asks us to take the limit as x approaches 2 of this rational expression that consists of h of 3x minus 7 over the sine of pi x. Oftentimes, a limit question on the AP exam free response question very well might use L'Hopital's rule, but we don't know that for sure. But what I've told my students time and time again is that, you really want to attack it the same way, whether it applies to L'Hopital's or not. So we can go ahead and split apart the numerator denominator and take those two limits separately. If it's a L'Hopital's rule problem, that's going to be something that's going to be necessary. And if it's not a L'Hopital's rule problem, then that process is still going to lead you to a correct answer. So that's the way that I want to tackle this. I want to go ahead and begin this process and take the limit as x approaches 2 of this numerator, h of 3x minus 7. And then I'm going to do the same thing here. I'm going to take this limit as x approaches 2 of this denominator. All right, now let's take a look at that first limit. Now, if we want to take this limit, we have this ability to plug in, directly substitute our value of x, but we have to make sure that we have a function that's continuous. Now, in this problem, if we kind of read through this a little bit, I believe that we could rationalize the fact that h is continuous. If we're talking about h being a definite integral of a twice differentiable function, and we can see from the graph, especially there at 2, that we're not going to have many issues with trying to combat continuity. And I think we could probably make that statement here. H of x is continuous. It's certainly going to be continuous at x equal 2. Now, from that statement, which is not a bad idea to write, because we did see a problem in the AP exam just a few years ago that did require a student to mention that before they inserted their x value. So if we let the x be 2, we end up with, what is this? H of 6 minus 7, I believe, which then means we have to figure out this value h of 6. Well, to do that, we would go to how we have defined our h, which is just simply a definite integral from 0 to 6 of that function f of t with respect to t. Then we subtract our 7, and then we just one more time go to our graph and figure out this signed area from 0 to 6. And it looks like we still have our good friend, right? 3 minus 5 plus 9, right? 3 minus 5 plus 9, and then we have to subtract that 7 afterwards. And once all of this is simplified, you do get 0. Now that in and of itself doesn't mean that L'Hopital's rule is potentially going to apply, but we're still looking at the chance that that might happen. Now we do the same thing for this denominator. Whoops. We do the same thing here for the denominator, and we let x be 2, and we have the sine of 2 times pi, which of course we know that to be 0. So now we have the ability to use L'Hopital's rule. One of Brian and I's favorite abbreviations for L'Hopital's rule is L''H. We know that it applies. And so we can actually perform L'Hopital's rule now. So L'Hopital's rule says that we can take the limit as x approaches 2 now of the derivative of the numerator over the derivative of the denominator. Now, taking the derivative of the numerator is going to invoke the chain rule here, right? H of 3x's derivative would be h prime of 3x multiplied by the derivative of 3x, which is just 3, which I'll put out in front. And then the derivative of minus 7 is 0. And then for the denominator, the derivative of sine of pi x, yet another chain rule, would be positive cosine pi x multiplied by the derivative of pi x, which is a pi out in front. Now if we plug in our 2, we would have 3 times h prime of 6 over pi times the cosine of 2 pi. And h prime of 6, well, what is h prime of 6? Well, remember, if h of x was defined up here as this integral, then the derivative is just going to use that fundamental theorem part 2 that we like to call it sometimes. H prime of x is just f of x. So this is the same as f of 6. And then that denominator, the cosine of 2 pi, if I'm not mistaken, I think that's going to be a 1. So 1 times pi is pi. And then f of 6, we can read that right off the graph. Right here he is, 8, and we have 24 as our numerator all over pi. Let's move on to part C. Part C we're going to be able to take, I think, fairly quickly here because it's a very standard question that we tend to see often, but that doesn't mean that it's a difficult question, and it doesn't mean that it's unimportant. If we see questions kind of repeatedly appearing on AP exams through the year, it probably means that there's a very wealth of value surrounding that particular problem. In this case, it says find any x value where h of x has a relative max. Give a reason for your answer. Well, with any function that we want to find a relative extrema for, we've been all trained that we need to take the derivative of that function, right? And then we would end up finding the critical values. Well, as I said before, h prime of x is just going to be f of x, right? By using that fundamental theorem part 2. What I just wrote is a very important part of this solution, and quite often will earn a point just by itself on a traditional free response question. Now, if we want this to be set equal to 0 to see where we have critical values, we simply look at the graph and think, well, where is f of x equal to 0? And I see 3 nice locations right here at 0, 2, and 4. It's not really worth our while to investigate where f is undefined because we don't see any breaks, holes, discontinuities on that particular graph. Now we just have to analyze what's the behavior of the function f around those points. And we find here at point 0, f has a positive value on this side and a positive value, which means the derivative of h is positive and positive, so no relative extrema there. But at 2, we have a positive sign to a negative sign of our f. And then at 4, we have a negative to a positive. So there are extrema at both 2 and 4, but this problem is only interested in the relative max. So we could simply say h of x has a relative max. I'm going to go ahead and abbreviate at x equal 2. And we want to give a reasoning for that. And maybe the best reasoning would be the fact that h prime of x, you can reiterate the fact that that's equivalent to f of x. You don't have to since you've already stated it here, but it's going to be important that you have it in at least one place. And to just mention that we have that sign change. We change signs from positive to negative. Positive to negative. And I am going to go ahead and turn this over to Brian to finish up BC2.
Awesome. So that was just in the nick of time there. We got the bell was ringing in the background. So we're good to go here. So we're going to look at part D. What would be a BC problem on here without looking at a couple of BC ideas, right? And so, and what would a BC exam look like without a Taylor polynomial? So again, one of the things that you're probably going to see every day this week is going to be a Taylor polynomial because it's certainly a really important topic for Calc BC, and we want to make sure that we have a chance to keep practicing it in different contexts, right, until it becomes really, really comfortable for you. So find the second degree Taylor polynomial for h of x centered at x equals -2. And if you've been following along, we've done several of these. And so I'm going to accelerate sort of the teaching side of this and kind of just give you a couple of reminders, right? Whenever you see a Taylor polynomial, a good thing to do is just to write down the degree, that's our n value, so our n equals 2. Make sure you pay attention what function you are approximating it to, because sometimes you have more than one function in the problem. And then finding the center is always going to be the other key idea. And then once we have that, if you've been watching me, you know that I like to create a template. Again, before I even try to find values and plug them in, I like to set things up to avoid any mistakes, because you might not make mistakes hardly ever. But during a timed pressurized test, right, like we're going to see on the AP exam, you might be going a little bit quicker than normal. Your blood pressure might be raised a little bit because you're a little bit nervous or anxious. And so you want to put some things in place that will prevent you from making silly mistakes on the exam that you normally wouldn't make on a normal day, right? So it's not about what you know now, what mistakes you might make now. It's about putting yourself in the best possible position during the real testing environment to avoid those mistakes, right? So we don't want to lose points because of our pride. We don't want to say, I would never make that mistake. I'm not going to show that work, right? Because I can do it in my head, or I don't ever make that mistake. Well, it's okay that you normally wouldn't, but do things a little bit more cautiously. That way we have no doubt about your performance. And so if we're trying to make a second degree Taylor polynomial, I like to call my polynomials P sub 2 or T sub 2 for second degree, but then I always write the template out first before I plug anything in. And so since we're doing it for h at -2, it's just going to be h of -2 plus h prime of -2 times x plus 2 plus h double prime of -2 times x plus 2 squared over 2 factorial. So that's always the template that I write down. And then it reminds me, okay, now I need to go back and all of those coefficient pieces, the h prime, h double primes, that's the part that I'm responsible for figuring out, right? And then I can go back and say, okay, what do I have? A graph, an equation, what do they tell me? But at least it gives me something to look for, right? It gives me a map of what I'm looking for. And so that's kind of giving me a head start. One other pointer that I might mention, this is what I tell my own students, whenever a problem in the STEM, right? The STEM, not literal STEM, Tony, but like the informational part of the problem, whenever it gives you a function defined by an integral, I tell my students, before we even read the questions, if that's in the STEM, we're going to go ahead and use that second fundamental theorem right off the bat. Before I do anything else, I know if I see h as the integral of f, I'm going to go ahead and use that second fundamental theorem to figure out how I can make a relationship here without the integration sign. So h prime is just going to be f, and then we're going to do it again to take the second derivative. So h double prime in this case is just going to be f prime. I do that up front because I know if they have the integration problem, one or both of those two pieces are probably going to show up somewhere in the problem. And so I want to make sure I have them kind of locked and loaded, ready to go for when I need them. So that's the first thing we always do. It also gives us some comfort level that on these problems, I don't have to sort of freak out when I read the first part and be like, I don't even know what to do on this problem, right? It gives us sort of an entry point into any question that involves an integration sign. It's, okay, we're going to go ahead and differentiate this twice so we can have h prime and h double prime. Now I have some comfort level. All of those memories of doing all these problems start to flood back in your head. All this muscle memory and brain memory of doing similar problems kind of starts to resettle. And so when you start seeing the problems, they start to kind of make a little bit more sense. Oh yeah, we've done problems like this before, but it gives you a nice entry point. So at least you know, okay, I can do something off the bat before I start jumping into the problem. So we have to now figure out what all of these values are, right? H of -2, H prime of -2, and H double prime. Well, luckily we have formulas for all three of those, our H equation, our H prime, and our H double prime. And so if we figure out what H of -2 is, right? H of -2, according to our formula, is just the integral from 0 to -2 of f of t dt. Well, I don't like those limits being reversed like that. So I'm going to go ahead and flip them using our properties of integration and say this is just the negative integral from -2 to 0 of f. Well, from -2 to 0, we're looking at this part of the graph, right? We're given a graph of f, and so the integral, right, of f, the definite integral would just be the signed area between the curve and the x-axis. So that's just going to be 10, and then with the negative sign in front becomes -10. And then I want to find h prime of -2, that second piece here. And h prime of -2, well, since I already have my equation, that's just going to be f of -2. Okay, well, that's going to be f of -2 is this point right here. And now we get a little bit trickier. How am I going to figure out that point? And so when we read the information, it says that -2, this is the tangent line, right, to the graph at -2. So if you recognize this equation of a tangent line and we can pick out some information, we know two things. Number one, the slope of the tangent line is 4, right, in front. And then the point on the graph is -2 comma 5. We can pull that information out from the equation. And so if I want to find f of -2, that's just a point on this graph. Well, it happens since that's the tangent line at -2, the tangent line and the graph of f share that point in common, right? It's the point of tangency. So if -2 comma 5 is this point on the tangent line, that's also going to be the point on the graph of f. And then finally, h double prime of -2 is going to be f prime of -2. And so now we're trying to figure out not the point on this graph of f, but now we want to figure out the slope of this graph of f. Well, f prime is the slope of f, which is the connection to the slope of the tangent line at that point, right? And luckily, since we have our tangent line, we also know the slope of the tangent line is 4, which means the derivative of f at that moment must have been 4. So a lot of kind of cool connections in that problem. And once we have all of those things laid out, we can just plug them into our Taylor polynomial, and we're going to see -10, and then plus, I'm going to plug in 5, x plus 2, and then h double prime was 4. And that's going to be x plus 2 squared over 2 factorial. And of course, you could reduce the factorial of the 4, but a time test, we don't have to. And to show you that, because we're already at 9:51 in the morning, I'm going to go ahead and leave that unsimplified, so that way we can jump into part E of this problem. So another good Taylor polynomial problem in a little bit different of a context, just getting us more and more reps with how we can handle these problems, right? And so finally today, we're going to skip part F on the worksheet, but I do want to do E because we haven't ever seen a problem like this on these live sessions. This is the first real implicit problem we've done. So consider the curve y squared plus 2xy minus x equals h of x. What in the world is going on with that h of x? Okay, find the slope of the line tangent to the curve, right? Think about what that phrase means. The slope of the line tangent to something means find dy over dx, right? We're trying to find dy over dx of this equation right here at the point 6, 1. Well, if I want to find a derivative or a slope, a good start would be to just take the derivative, right? So this is an equation, and just like before with the second fundamental theorem, we can just take the derivative of both sides, right? But it's going to require us to use implicit differentiation. And so if I go ahead and differentiate this, we have our y squared term. So what's y squared's derivative? Well, it's going to be 2y, right, using our basic derivative rules. But we can't forget that chain rule of multiplying by dy dx, because we're taking the derivative with respect to x. We have to have that little chain there. Plus, now this 2xy term, we got to be careful because it's so easy to just want to take both of those derivatives at the same time, but we're going to be having to use the product rule, right? So I love this problem because it's intertwining a lot of those derivative rules that we've been practicing, product rule, chain rule, things like that. So we're going to take the product rule. I'm going to consider the first piece to be 2x and the second piece to be y. So 2x's derivative is going to be just 2. We'll leave the y the same. And then plus, now I'm going to leave that 2x the same, and then take y's derivative, which is going to be dy over dx. And then minus, well, x's derivative becomes 1. And then this thing, well, what's h of x's derivative? Well, you know what it is? It's just h prime of x. It's already in terms of x, so I don't have to multiply by, d something over dx, as h of x is already in terms of x. So it's just going to be h prime of x. And we're trying to find dy dx. So this is stuff that you've done before, just probably not with an h of x on the other side. Normally you'd have like a constant or a number over there, right? So it's just got a little bit of a twist to it. But let's just go ahead and try to get dy dx by itself. If it wants me to find dy dx, let's go ahead and isolate those. And I'm going to do this in a couple of shorter steps than maybe normally we would because of time. But I know I have two terms that have dy dx. So if I think about grouping those two terms and factoring out the dy dx, I would have a 2y plus 2x left, right? And then these other two pieces, this 2y and the 1 that don't have a dy dx, let's just assume I had brought them to the other side of the equation. So that's going to be h prime of x plus 1 and then minus the 2y. And then from here, I can just divide, right, to get my dy over dx. dy over dx is going to be h prime of x plus 1 minus 2y, and then divided by that quantity, 2y plus 2x. And that's our dy dx. And it wants me to find that at the point 6, 1. So x is going to be 6, y is going to be 1, right? So we could plug in 6 for x. Even in the h prime, we can plug in 6, right? So h prime of 6 plus 1 minus 2 times 1 all over 2 times 1 plus 2 times 6. And we're almost there. We can't leave our answer like that. We don't have to simplify, but we can't leave things with h in the answer, right? So we have to figure out what is h prime of 6. Well, that's where that expression h prime comes in handy. H prime of 6 is just f of 6. And looking at the graph of f, we see f of 6 is just going to be equal to 8. And so our final answer is going to be 8 plus 1 minus 2 all over 2 plus 12. Don't need to simplify that, but if you did simplify that, it would all turn out to a beautiful 1/2. Isn't that a cool problem? Isn't that kind of a neat twist on doing implicit way back earlier in the year with kind of a different approach to it? So this is the kind of examples that I think will really prep you for the exam, is just seeing some things that you've done before, but maybe in some different, unique, twists that you haven't seen before. If you can do these kind of problems, then you truly understand these ideas, and you know how to approach problems that maybe you haven't seen before, just by breaking them down and taking what you know and applying it to that. So, like I mentioned, we're gonna skip F, but man, I love F. I wish we could have gotten to it. So try it and then check your solutions. I'll be curious to see how many students are able to solve F. So we want to jump to our tweets of the day. Tweets with Tony. Tony, what do you have today?
Well, I have got a couple of tweets that are going to recognize the beautiful Windy City. Brian and I have had the opportunity to work with many teachers from Chicago area, and there's so many great teachers and students there. So for our AP Teachers Rock, Ms. Becker from Lane Tech College Prep High School has been the best AP Calculus BC teacher. She's made the class so much fun and helped me develop a true love for math. So congratulations to those students around the near north side of Chicago at Lane Tech Prep and Ms. Becker. AP Students Rock. Well, we know that we have some wonderful students because they are making some flip grid videos to explain parts of our awesome problems. Who are those students? They are the students from Maine Township High School, right in Park Ridge, Illinois, which I think is kind of close to the Des Plaines area. And their teacher is a fantastic teacher, Ms. Elizabeth Ball. So we want to thank you for recognizing your teachers and your students, and the fact that your students do indeed rock. Looking ahead, I think we have some wonderful things coming up. Tomorrow, we're going to talk about the algebraic stems that connect AB to BC. I may not make a trip to my garden for that now that I know better. And of course, next week, we have our AP Prep Week.
Awesome.
Dogs and cats.
Yeah, pets of the day. Don't forget, keep tweeting us out at PasswaterB, at AP Calc Teacher. Send us your pets. I asked for some pets besides dogs and cats. I knew you had them and you delivered. So we got 3 more entries today that I want to share. No dogs today. I need some more dogs. Give me some more cute dogs. But we've got Cherik the cat, a friend of mine and friend of Tony's. Karen Hires, a fellow AP Calculus teacher and reader, has her friend, her cat Cherik, who says goes on a walk with her every day. I wish I could convince my cats to walk with me outside. They would just run away. And then we have some chickens, lots of chickens that got sent in. So this middle one came from Fiorella, which is 4 chickens. Nugget, Lacey, Digger, and then Half Nugget are in the picture. I'm afraid to ask what's going to happen with Nugget and Half Nugget in the future. It's not a very promising name. And then also Becky sent us in her chicken Barb. This is what I love, Tony. Barb is named Barb after her amazing calculus teacher. So it's almost like a pet of the week and AP Teachers Rock mixed into one. So I don't know. I'm assuming it's a compliment. She said amazing calculus teacher, right? So I'm assuming that she loves her calculus teacher. So what an amazing tribute. None of my kids name their pets after me. I don't know about you, but that's it for us. You guys have been awesome as usual, and we're looking forward to tomorrow, another great day of algebraic stems. Tony, final thoughts.
Stay safe, everyone. Keep learning.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes, AP Calc.